Okay, Chem scholars, today's part has to do with the idea of periodicity. And before I explain what that means, let's go to the root of it and talk about periodic, right? We have this periodic table. What is periodic? Okay. Well, I threw the definition up there because we're talking about things that occurs in intervals, something that has established patterns and will repeat and so on. And that's what we really want to focus on with the periodic table, the fact that properties can be predicted based on where they are in the table and that they repeat, right? We put the elements into columns that we call families because they have similar properties. So because of that, we really should be able to make a number of predictions just based on where something is on the table. Now, remember that these are general trends. There are exceptions for a lot of reasons that may involve some chemistry we are not ready to get into. I don't want you to worry about the exceptions right now. I just want you to get the general idea, the general trends. Okay? So let's talk about that a little bit. Okay? One of the most important things that is physics related is the concept of electrical attractions and repulsions. Okay? Really basic ideas. You've played with magnets before. It's kind of same ideas because magnets have a north and a south. Well, charges have plus or minus. So there are opposites. And we know that opposites attract and likes repel. Very important to what we're going to talk about in this unit. And it's a pretty simple idea. Also, if you played with magnets, you know that the pull of the magnet gets stronger when they get closer together. Distance is a factor. A bigger distance means a weaker pull. A shorter distance means a stronger pull. Okay, so distance is inversely related. That's important as well. Okay, so that's kind of where we're going to be talking about as we go into these ideas. Now, in terms of attractions and repulsions or pushes and pulls, okay, we're talking about protons and electrons, right? We know that protons are in the nucleus and electrons are being pulled inwards by them. Okay? We know that electrons will repel other electrons. Now keep in mind that the electrons have a lot more freedom to move, whereas the protons are locked into the nucleus with the neutrons. Okay, the neutrons are like the glue holding that nucleus together. Okay, there's no glue on the outside, so the electrons are going around. So they're the ones that are more able to move, and that's why we talk about them being pushed or pulled. Okay, so if we look at an atom and we think about the electrons in one of the valence shells, okay, those are being pulled in by the electrons, by the protons in the nucleus, but they're also being pushed out at the same time by the other electrons. Okay, so there's a little bit of competition there. Okay, the inner electrons are sometimes referred to as shielding electrons because they kind of block the effect of the nucleus. Okay, let me explain what I mean there. I'm going to shift views. And we're going to go to the board here real quick. Okay, so if we were to talk about an atom of, let's say, let's keep it simple, lithium. Okay, lithium has one valence electrons. It has 2 electrons in the first energy level. Okay, this electron is being pulled by the 3 protons in the nucleus. Okay, so it's this one, so it's this one. They're all getting pulled by the protons. Okay, but let's focus on this one for a moment. But the problem is that these 2 are going to be pushing that electron away. So it's getting pulled in by 3 protons, being pushed away by 2. So it loses some of the effects of pull. Okay, the protons are being worked against by the electrons, and so the pull isn't quite as strong as it could be. Okay. We just have to understand that this shielding effect goes on, and it does kind of affect the nucleus and how strong it pulls. Okay, so let's go back to there. All right, so now same idea. Let's look at this diagram with sodium. Okay, how many protons are pulling on either electron in the first energy level? So we're talking about this electron here, this electron here. Well, obviously, all 11 protons, because protons don't do man-to-man defense, okay? Protons don't know what they're pulling. They just exert an influence on any charge. So any of the electrons around are being pulled by the 11 protons, okay? And that's kind of the emphasis here. So they're all being pulled by 11 protons. It doesn't matter. Now, again, there is shielding. So this one out here, for example, the valence electron, It's not really getting pulled as well by the 11, but technically all the protons are pulling on all the electrons. Okay? Same idea then if we talk about magnesium. Except magnesium has 12 protons, so each electron is being pulled by 12 protons. Okay? Same thing if we talk about aluminum. Now it's 13 protons though. So each electron is being pulled by 13 protons. Okay? Now I know that seems a little redundant. I'm just trying to emphasize the point that, again, they all get pulled by the nucleus. Okay? So let's compare them. We said that sodium had 3 energy levels and every electron is being pulled by 11 protons. We said that magnesium has 3 energy levels and all of its electrons are being pulled by 12 protons. And we said that aluminum has 3 energy levels and its electrons are all being pulled by 13 protons. Well, what's going to be stronger? 13 protons, 12 protons, or 11 protons? I hope you understand that it will be 13 protons. So the nucleus in aluminum is stronger than the nucleus in magnesium, and that's stronger than the nucleus in sodium. Okay? So as we look at the periodic table, shift around here, okay, and shift to view again. Okay? I'm talking about these elements here, right? So I talked about sodium, magnesium, aluminum. They're all in the third row of the periodic table, so that means they all have 3 energy levels. So we're comparing things that are similar. It's important that we don't throw too many variables in there at once. They're all in the same row. And we just said that aluminum is stronger than magnesium, which is stronger than sodium. So what about silicon? Well, that would be stronger still. What about phosphorus? That would be stronger still. What about sulfur? That would be stronger still. Chlorine would be stronger. And then argon would be the strongest in that row. Okay? Now, if it's stronger, well, let's talk about what that means. So, if the electrons are being pulled inwards, and we know that argon's electrons are being pulled in strongest of anything in that row, what does that say about the size of the atoms? All right, well, let's focus, like the slide says, just on sodium, magnesium, aluminum. We already established that aluminum had the strongest nucleus of those 3. So if it's stronger, what's it doing to the electrons? Pulling it inward. So what's that going to do to the size? It's going to shrink it. Okay? So one trend that we're going to talk about is the idea of atomic size or radius. Okay? As we compare elements from left to right, because the nucleus is getting stronger, the size is getting a little smaller. And you see that on the graph here. At first, some of the jumps are kind of significant, and down here, the jumps are kind of small. That's not the issue. We're just trying to say if it's bigger or smaller. And you can see that as you go from left to right, from sodium to magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, the size is decreasing. Okay? So atomic radius or atomic size decreases as we compare elements from left to right. Okay? Now, what about as we compare them from top to bottom? I mean, if the logic is stronger nucleus, well, now what nucleus is stronger? Let's take the noble gases. Helium, neon, argon, krypton, xenon, radon. Okay? Now, the problem is they have different numbers of energy levels. Okay? So when we compare radon, okay, we're talking about 6 energy levels. Helium only has 1 energy level. Okay? It's a little hard to compare this electrical pull because the distance and the amount of charge is changing. So let's just talk about it from energy levels. An energy level is a ring around the nucleus. So more rings has got to be more size. So it should make sense that from top to bottom, the size increases. And you can see that here for pretty much every family. As you go down, the size is increasing. Okay? So the trend is clearly left to right, size is decreasing. Top to bottom, size is increasing. So now, where do you think the smallest element is? Well, if we look at our chart there, it says clearly helium is, right? Well, that makes sense because to the right it gets smaller, and then you go down it gets bigger. So that means the top right has got to be the smallest element, and bottom left should be the largest element. So francium is the largest known element. It's radioactive though, so that's why you don't see it on this table here on the slide. Okay, but that's what we're looking at for the radius. Okay, so here's a chart showing most of the periodic table. You'll notice that there are exceptions. Okay, that's why I threw this up here. We don't care about the exceptions. Okay, don't worry about that. but we have to recognize that it does happen. If you go on in chemistry, you'll start to talk about why there are exceptions. And at some point this year, we'll hint at a couple of them, but we're not going to get too involved in them. Okay. So again, here's another chart just to try and make it a little bit more obvious, a little bit easier to read, but again, same idea. Okay, we're going to pause there and go do a little activity. We'll pick up on energy in the next video.